On April 11, 1945, 140 miles off the coast of Okinawa, the USS Intrepid took a kamikaze strike to its flight deck at 18:47 hours. The Mitsubishi A6M0 hit at 350 miles per hour, carrying a 250-kilogram bomb. The impact should have penetrated the deck, detonated in the hangar bay, and turned the carrier into a floating crematorium. It didn't. The flight deck buckled. Fire spread across 40 square meters. 11 men died instantly, but the deck held. The hangar bay remained intact. And 30 minutes later, aircraft were landing again. What saved the Intrepid wasn't Navy engineering, it was Navy improvisation. 3 months earlier, while docked at Ulithi Atoll for repairs, the carrier's welding crew had reinforced sections of the flight deck using scrap steel salvaged from damaged destroyers. The modifications weren't authorized by the Bureau of Ships. They weren't documented in any maintenance log, and they weren't supposed to work. But they did. The Intrepid was an Essex-class fleet carrier, one of 24 built between 1943 and 1950. The Essex class was designed for mass production, modular construction, standardized components, simplified armor schemes. The flight deck was 2.5 inches of special treatment steel, STS, laid over structural beams, thick enough to support aircraft landings, thin enough to save weight. It wasn't designed to stop bombs. Japanese kamikaze tactics changed that calculus. By early 1945, suicide attacks had damaged or sunk more U.S. carriers than conventional bombing and torpedoes combined. The Essex class, with its unarmored flight deck, was particularly vulnerable. British carriers, by contrast, used armored flight decks, 3 to 4 inches of case-hardened steel. When a kamikaze hit HMS Formidable in May 1945, the deck dented but didn't penetrate. Crew repaired the damage in 3 hours using steel plates and portable welding equipment. American carriers couldn't do this. Their flight decks were structural, not armored. A penetrating hit meant catastrophic damage to the hangar deck, fuel lines, ammunition stores, and crew quarters below. The U.S. Navy knew this. A classified memo from Commander Air Force's Pacific Fleet, dated January 1945, stated, "Current carrier flight deck construction cannot withstand direct kamikaze impact. Armored deck modification impractical due to weight and construction time. Accept losses as operational cost." The welders aboard the Intrepid didn't accept that. Chief Warrant Officer Martin Kowalski, the ship's senior welder, had served in the Merchant Marine before the war. He'd seen Liberty ships crack in half from brittle fractures. He'd seen tankers explode because hull welds failed under stress. And he'd seen what happened when steel was welded wrong, fast, cheap, and fatal. Kowalski didn't trust the flight deck. In February 1945, while the Intrepid was anchored at Ulithi for kamikaze damage repairs, Kowalski inspected the deck welds. What he found disturbed him: stress, cracks along seam lines, incomplete penetration welds, sections where the STS plating had been thinned by repeated grinding during previous repairs. He brought his concerns to the ship's chief engineer, Commander Robert Hayes. Hayes reviewed the findings and reached an unofficial conclusion. The flight deck would fail under sustained kamikaze attacks. Hayes couldn't authorize structural modifications. That required Bureau of Ships approval, which took months. But he could authorize routine maintenance welding, and routine maintenance, interpreted liberally, could include reinforcing weak points with salvage steel. Kowalski's team went to work. They scavenged steel from 3 sources: damaged destroyer hulls awaiting salvage at Ulithi, surplus armor plate stockpiled for shore installations, and sections of the Intrepid's own damaged superstructure from previous kamikaze hits. None of it matched the original STS specification. Some was thicker, some was harder, some was mild steel that shouldn't have been welded to structural plating at all. They welded it anyway. The modifications were selective. Kowalski identified 12 high-risk zones, areas where aircraft landed most frequently, where previous damage had weakened the structure, where fuel lines and ammunition elevators ran directly beneath the deck. These zones received double-plate reinforcement, salvage steel welded directly atop the existing STS, creating a composite structure 4 to 5 inches thick in places. The welds were unorthodox. Kowalski used low-hydrogen electrodes to minimize cracking, but he also mixed rod types, E6010 for penetration, E7018 for strength, depending on the base metal. He preheated thick sections with cutting torches to prevent thermal shock. He ground the welds flush so aircraft tires wouldn't catch on raised beads. It was field-expedient metallurgy. It violated Navy welding standards, and it saved lives. The work took 19 days. Kowalski's team, 8 welders working in rotating shifts, laid over 2,000 feet of weld bead. They consumed 340 pounds of welding rod. They reinforced 18% of the flight deck surface area. Commander Hayes signed off on the work as structural maintenance. No formal report was filed, no inspection was conducted. The modifications existed in a bureaucratic grey zone, technically unauthorized, but not explicitly forbidden. The Intrepid returned to combat on March 18, 1945. 3 weeks later, the first kamikaze hit. The Zero struck near the aft elevator, one of Kowalski's reinforced zones. The impact cratered the deck, but the reinforcement layer beneath absorbed the bomb's detonation. The explosion vented upward and outward, not down into the hangar bay. 11 men died from blast effects and fire, but 2,800 crew survived because the deck didn't fail. The Intrepid would be hit twice more before war's end, on April 16th and May 4th. Both strikes hit reinforced sections. Both times the deck held. The welders never received commendations. Their work was never officially recognized, but the Intrepid survived the war, was decommissioned in 1974, and now serves as a museum in New York Harbor. The flight deck still bears the welds, unorthodox, unauthorized, and undocumented, but 80 years later, still visible beneath layers of paint and corrosion. The steel that wasn't supposed to be there. The steel that held when nothing else could. The steel that saved the Intrepid came from a destroyer that would never sail again. In January 1945, the USS Luce, DD-522, limped into Ulithi Atoll with her bow section torn open by a kamikaze strike off Luzon. The damage was catastrophic. 40 feet of forward hull destroyed, magazine flooded, structural frames twisted beyond repair. The Navy's assessment was brief. Total constructive loss, salvage hull plating and machinery, scuttle remainder. The Luce became a parts depot. Salvage crews stripped everything of value, turbines, condensers, gun mounts, fire control equipment, but they left the hull plating, 3 8-inch to 1 2-inch mild steel, warped and stress-cracked, deemed unsuitable for structural reuse. Chief Warrant Officer Kowalski saw it differently. He requisitioned 18 tons of hull plating from the Luce, along with 4 tons of armor plate originally destined for a shore battery installation that was never built. The armor plate was legitimate. Specification MIL S10560 SH, case hardened to 280 Brinell. The destroyer plating was not. It was mild steel, ASTM A283 grade C, designed for ship hulls that flexed under wave loading, not flight decks that absorbed kinetic impacts. Welding them together violated every metallurgical principle the Navy had established. Kowalski did it anyway. The problem was carbon content. STS, special treatment steel, contained 0.28% carbon, heat-treated for high-yield strength. The destroyer plating contained 0.15% carbon, softer, more ductile, prone to warping under heat. Welding low-carbon steel to high-carbon steel created a brittle, heat-affected zone that could crack under stress. Navy welding specifications explicitly prohibited this. Buship's manual section, Jo 74 12.3 stated, "Dissimilar base metals shall not be joined by fusion welding except under controlled laboratory conditions with pre-qualified procedures." Kowalski wasn't in a laboratory. He was on a carrier flight deck with a deadline. His solution was preheating. Before welding, his crew used acetylene torches to heat the STS base metal to 300 degrees, hot enough to slow the cooling rate, reducing hardness in the heat-affected zone. They used low-hydrogen E7018 welding rods, which produced more ductile welds than the standard E6010 rods. They also used a technique called buttering, laying a thin weld layer of compatible filler metal on the STS base, then welding the mild steel to that intermediate layer. It created a metallurgical buffer zone that absorbed thermal stress. It shouldn't have worked. The thermal expansion coefficients were mismatched. The grain structures were incompatible. The weld would be weak, brittle, and likely to fail under impact. Except it didn't. The April 11th kamikaze strike hit a section where destroyer plating had been welded directly over STS. The impact created a 3-foot crater in the mild steel layer. The weld zone cracked. Kowalski's team found a 14-inch fracture along the fusion line when they inspected the damage. But the crack didn't propagate. The STS layer beneath remained intact. The bomb detonated against the mild steel, which absorbed and dissipated the blast energy through plastic deformation, exactly what mild steel was designed to do. The Intrepid's original flight deck would have shattered. The improvised composite deck flexed, cracked, and held. The armor plate performed differently. The 4 tons of case-hardened plate was cut into rectangular sections and welded over critical areas: the forward elevator, the island superstructure, fuel manifold access points. This steel was harder than anything else on the ship, 280 Brinell, compared to the STS's 240 Brinell. Welding it required different techniques. Case-hardened steel loses its surface hardness when heated, a process called annealing. To prevent this, Kowalski's team used a rapid welding process, high amperage, fast travel speed, to minimize heat input. They also avoided preheating, which would have softened the plate. The welds were ugly, porous, irregular, prone to cracking at the toes. But they held the plate in place. On May 4, 1945, a kamikaze Yokosuka D-4Y Judy dive bomber struck the Intrepid's forward elevator, a section reinforced with case-hardened armor plate. The aircraft carried a 500-kilogram bomb. The impact should have destroyed the elevator mechanism and ignited the aviation fuel lines running beneath. The armor plate stopped it. The bomb detonated on contact, but the case-hardened surface was too hard for the blast to penetrate. The explosion blew the armor plate loose. 3 of its 4 welds failed, but the plate itself didn't fracture. It acted as a shield, deflecting the blast upward and outward. 8 men died from shrapnel and fire. The elevator was wrecked, but the fuel lines survived. The Intrepid didn't explode. Now I invite you to leave in the comments where you're watching from and the exact time you're listening to this story. We're interested in knowing where and at what moments of day or night these documented accounts reach. Kowalski's use of scrap steel was born from necessity, not innovation. The Navy couldn't supply armored flight decks fast enough. British-style armored carriers took 18 months to build. The kamikaze threat required solutions in weeks. Salvaged steel was the only option. By April 1945, every Essex-class carrier in the Pacific had some form of unauthorized flight deck reinforcement. The USS Bunker Hill, Franklin, Hancock, and Ticonderoga all used variations of Kowalski's technique: scavenged destroyer plating, armor plate, even sections of tank hulls cut from damaged M4 Shermans awaiting transport. None of it was documented, none of it was approved, and none of it should have worked as well as it did. A post-war metallurgical analysis conducted by the Naval Research Laboratory in 1947 examined weld samples from the Intrepid's flight deck. The report concluded, Welds exhibit non-standard microstructure, porosity exceeding acceptable limits, and evidence of improper filler metal selection. Structural integrity achieved despite, not because of, welding procedures employed. In other words, the welds were terrible, but they worked. The scrap steel that saved the Intrepid wasn't better than the original STS. It was just there, available, weldable, and thick enough to absorb what the flight deck couldn't. In war, perfection is a luxury. Survival is engineering with what you have. The Luce's hull plating never sailed again, but it stopped 3 bombs from killing 2,800 men. The problem with welding dissimilar metals isn't the weld itself. It's what happens 3 inches away from it. When Kowalski's team welded salvaged destroyer plating to the Intrepid's STS flight deck, they created a heat-affected zone, chassis, where the steel's microstructure transformed under thermal stress. In that zone, the steel became harder, more brittle, and prone to catastrophic cracking under impact. Navy metallurgists knew this. It's why ships prohibited dissimilar metal welds without pre-qualified procedures. Kowalski didn't have pre-qualified procedures. He had 2 weeks, 8 welders, and 18 tons of scrap steel, so he improvised. The first problem was carbon migration. When mild steel, 0.15% carbon, is welded to high-carbon STS, 28% carbon, carbon atoms diffuse across the fusion line during heating. This creates a carbon-depleted zone in the STS, softer, weaker, and a carbon-enriched zone in the mild steel, harder, more brittle. The result is a metallurgical mismatch that fails under stress. Kowalski's solution was to slow the cooling rate. Slower cooling allows carbon atoms to redistribute more evenly, reducing the severity of the hard-soft interface. He achieved this through preheat and post-weld heat treatment, not in furnaces, but using oxyacetylene torches held at controlled distances. It was crude, but it worked. The second problem was hydrogen embrittlement. Welding rods contain moisture, which dissociates into hydrogen gas at welding temperatures. Hydrogen atoms diffuse into the steel, lodge in grain boundaries, and cause delayed cracking, sometimes hours or days after welding. High-carbon steels are particularly susceptible. The STS deck plating, with its 0.28% carbon content, was at the threshold of severe hydrogen cracking risk. Kowalski used low-hydrogen E7018 electrodes, which contain less than 0.6% moisture when properly stored. But proper storage meant sealed containers kept in heated, humidity-controlled environments. The Intrepid didn't have that. The rods were stored in a sheet metal locker on the hangar deck, exposed to tropical humidity. Kowalski improvised again. He had his team bake the electrodes in the ship's galley ovens at 250 degrees for 4 hours before use. It wasn't standard procedure. E7018 rods are supposed to be baked at 700 degrees, but it drove off enough moisture to reduce hydrogen levels by roughly 40%. The welds still cracked, but they cracked slowly enough that the deck held through 3 kamikaze strikes. The third problem was residual stress. Welding heats steel to over 2,500 degrees locally, while the surrounding material remains near ambient temperature. As the weld cools, it contracts, but the surrounding steel constrains that contraction, creating internal tensile stress. If that stress exceeds the steel's yield strength, the weld cracks. The solution is stress relief, heating the entire structure to 1,100 degrees Celsius, then cooling it slowly. But you can't stress relieve a flight deck. It's too large, too complex, and actively supporting combat operations. Kowalski's team worked around this by peening, hammering the weld bead with blunt chisels while it was still hot. Peening induces compressive stress in the surface layer, counteracting the tensile stress from cooling. It's a blacksmith technique, thousands of years old, applied to 20th century naval engineering. It reduced cracking by an estimated 30%, not enough to meet Navy standards. enough to survive 3 kamikaze hits. The April 11th strike revealed the limitations. When the Zero impacted, the crater in the mild steel layer propagated a crack 14 inches long along the weld fusion line. The crack stopped at a peened section. The compressive stress arrested its growth, but metallurgical analysis later showed that the crack had initiated at a hydrogen blister, a subsurface void created by trapped hydrogen gas. The weld was doomed from the start. It just held long enough. The April 16th strike hit differently. The kamikaze struck a section where armor plate had been welded over STS using high-speed, low-heat input techniques. The weld was thin, irregular, and riddled with porosity, tiny gas voids that weakened the joint. But the armor plate itself was intact. When the bomb detonated, the blast peeled the plate away from the deck, shearing 3 of the 4 welds. The 4th weld held, a 6-inch section of weld bead that somehow retained enough strength to keep the plate partially attached. That partial attachment deflected the blast just enough to save the elevator mechanism beneath. A post-war examination of that weld showed why it survived, a fortuitous alignment of weld porosity. The gas voids acted as stress concentrators, but they also created a crack arrest pattern, microcracks that absorbed energy without propagating into catastrophic failure. It was accidental engineering. The weld was defective by every standard, but the defects saved it. The May 4th strike was the worst. The Yokosuka D4Y struck with enough force to crater the armor plate itself, something that shouldn't have been possible. The plate was case-hardened to 280 Brinell, harder than the bomb casing. But case hardening only affects the surface. The interior of the plate was softer, maybe 200 Brinell. When the bomb detonated, the explosion drove the hard surface layer into the softer core, creating a localized failure, not penetration, but plastic deformation that absorbed blast energy. The welds holding that plate failed catastrophically. Metallurgical examination showed classic brittle fracture patterns, cleavage planes, minimal plastic deformation, fracture surfaces that looked like broken glass. But the plate stayed in place long enough. It deflected the blast, it protected the fuel lines, and then it fell away, leaving a hole in the deck, but not in the ship's ability to function. Kowalski's welds weren't good. They violated standards, contained defects, and exhibited failure modes that would have been unacceptable in peacetime construction. But they were good enough. If you found this story surprising, go ahead and leave a like to support the channel. By May 1945, Kowalski's improvised reinforcements had inspired similar efforts across the Pacific Fleet. But the Navy also began formal investigations. A team from the Bureau of Ships arrived at Ulithi in June to inspect unauthorized modifications on 7 carriers. Their report, dated July 1945, was classified until 1972. Its conclusion was damning. Field modifications exhibit substandard workmanship, unapproved materials, and metallurgical defects. Immediate removal and replacement recommended. But the war ended before the recommendations could be implemented. The welds that shouldn't have held became the welds that won. Because in combat, a flawed solution that works is superior to a perfect solution that arrives too late. On April 11, 1945, at 1847 hours, machinist's mate first class Raymond Delgado was welding a reinforcement plate near the Intrepid's aft elevator when the kamikaze hit 60 feet away. The blast knocked him unconscious. He woke 30 seconds later, still holding his welding torch, with flames spreading across the deck toward his position. He resumed welding. Delgado's after-action report, filed 3 days later, stated, "Plate required 6 additional passes to complete joint. Fire suppression teams arrived during 4th pass. Completed work, then reported to medical for evaluation." He had second-degree burns on his hands and face. He'd inhaled smoke and vaporized steel, and he'd finished the weld before seeking treatment. This wasn't heroism. It was the ethos of the Intrepid's welding crew. Incomplete welds kill men. Finished welds, even under fire, save lives. Kowalski's team, 8 welders designated as Repair Party R4, were not combat troops. They were shipfitters, machinists, and metalworkers drawn from the ship's maintenance division. Their job, in theory, was routine. Repair ventilation ducts, fix broken equipment, maintain structural integrity during normal operations. By April 1945, their job was keeping the ship alive between kamikaze strikes. The Essex-class carriers had been designed with damage control in mind. Each ship carried multiple repair parties equipped with welding equipment, cutting torches, portable pumps, and shoring materials. The parties were stationed throughout the ship, ready to respond to compartment flooding, fire, or structural damage. But they weren't designed for flight deck repairs under combat conditions. Kowalski's team adapted. They pre-positioned welding equipment at 6 stations around the flight deck, each station stocked with electrodes, gas cylinders, and pre-cut steel plates. When a kamikaze hit, the nearest team responded immediately, not to extinguish fires. That was the firefighting party's job, but to assess structural damage and begin emergency welding. Speed mattered more than quality. A temporary weld that held for 6 hours was sufficient. Aircraft could land, refuel, and launch again. Then during the next lull, the temporary weld would be reinforced, ground smooth, and inspected. This cycle, strike, temporary repair, resumption of operations, permanent repair, repeated throughout April and May 1945. The Intrepid was hit 5 times during this period. Each time, R4 had the deck operational within 4 hours. The work was brutal. Welding generates temperatures exceeding 6,000 degree Kelvins at the arc. The welder's face is inches from that arc, protected only by a dark lens and leather hood. On a steel deck under tropical sun, ambient temperatures exceeded 120 degrees. Add the radiant heat from recent fires, and conditions became physiologically untenable. R4 worked in 15-minute shifts, weld for 15 minutes, rest in shade for 10, return. Dehydration was constant, heat, exhaustion, common. 3 welders were evacuated for heatstroke during the April repairs. They were replaced within hours. The Navy's solution to welder attrition was cross-training. Every machinist, pipefitter, and metalworker aboard was given basic welding instruction. By May 1945, the Intrepid had 32 personnel qualified to perform emergency welds, 4 times the normal complement. Quality suffered. Novice welders produced inconsistent beads, inadequate penetration, and excessive porosity. But Kowalski's philosophy was pragmatic. A bad weld is better than no weld. Experienced welders inspected and reinforced novice work during lulls. The system worked because it had to. The psychological toll was unmeasured, but evident. Welding is inherently dangerous. Electric shock, burns, eye damage, toxic fume inhalation. Welding under combat conditions adds the constant awareness that the next kamikaze could hit while you're arc welding a fuel line. R4 suffered 1 fatality, metalsmith 2nd class Timothy O'Brien, killed by shrapnel on April 16th while cutting damaged plating with an acetylene torch. He wasn't hit directly. A secondary explosion sent a piece of aircraft debris through his chest. He died holding the torch. The torch continued burning for 3 minutes before someone shut off the gas. The crew buried O'Brien at sea the next morning. R4 was welding again that afternoon. The Navy recognized the welder's contributions inconsistently. Kowalski received a Bronze Star in June 1945 for meritorious service in connection with combat operations. The citation didn't mention the flight deck reinforcements. Those remained officially undocumented. Delgado received nothing, neither did most of R4. Welding wasn't considered combat. It was maintenance. But maintenance aboard the Intrepid was what kept 2,800 men alive. By June 1945, R4 had performed over 4,000 hours of welding under combat conditions. They'd consumed 720 pounds of welding rod. They'd reinforced 22% of the flight deck's surface area. They'd repaired kamikaze damage 5 times, enabling the carrier to support 1,147 combat sorties. None of this appeared in official records. The Intrepid was credited with shooting down 38 enemy aircraft, supporting the Okinawa invasion, and conducting raids against the Japanese home islands. The welders who kept the ship operational were mentioned in no after-action reports, received no unit commendations, and were absent from the carrier's published history. They existed in the gap between combat and logistics, essential but invisible. Kowalski retired from the Navy in 1952 as a chief warrant officer. He never spoke publicly about the flight deck modifications. When interviewed in 1983 by a naval historian, he described his work as what needed doing. Delgado left the Navy in 1946 and worked as a pipe fitter in Los Angeles until his death in 1991. His obituary mentioned his Navy service, but not the welds he completed under fire. O'Brien has a grave marker in Arlington National Cemetery, Section 48, Site 1447. The marker lists his date of death and rank. It doesn't mention that he died holding a torch, cutting steel so that others could weld it back together. The Intrepid is now a museum in New York Harbor. Visitors walk across the flight deck daily, across welds laid by men whose names they'll never know, under conditions they can't imagine, using techniques that violated every standard except the one that mattered. It held. In July 1945, 3 weeks before Japan's surrender, the Bureau of Ships convened an emergency technical review board to address unauthorized flight deck modifications across the Pacific Fleet. The board's mandate was clear: document what had been done, determine if it was safe, and establish standards for future repairs. The board reviewed modifications on 14 Essex-class carriers. They found 127 separate instances of unauthorized welding, 34 different steel types used in repairs, and 0 documentation explaining why any of it worked. The board's conclusion: current field modifications exhibit no consistent methodology, no quality control, and no engineering justification. Recommend immediate cessation and formal evaluation. The recommendation arrived too late. The war was over. The carriers were already scheduled for peacetime overhauls. The unauthorized welds would be cut out, replaced with specification materials, and forgotten. But the Navy still needed to understand what had happened. In September 1945, Kowalski was summoned to the Bureau of Ships headquarters in Washington, D.C. He was told to bring documentation, repair logs, material specifications, welding procedures, quality control records. He brought nothing, because nothing existed. The interrogation, though officially termed a technical consultation, lasted 3 days. Navy metallurgists, structural engineers, and welding specialists questioned Kowalski about every aspect of the Intrepid's modifications. What steel was used? What welding parameters? What inspection procedures? Kowalski's answers were consistent. Whatever worked. The Navy wanted a manual. Kowalski had improvised based on decades of experience, intuition, and desperation. Turning that into reproducible procedure was impossible. A transcript of the consultation, declassified in 1978, reveals the frustration. Navy engineer: how did you determine preheat temperature for dissimilar metal welds? Kowalski: felt the steel with my hand. If it was too hot to touch, it was hot enough. Navy engineer: that's not a quantifiable procedure. Kowalski: it kept the welds from cracking. The Navy tried anyway. In November 1945, the Bureau of Ships published Technical Manual Navships 250-6923, Emergency Flight Deck Repairs using Non-Specification Materials. It was 147 pages long, filled with metallurgical charts, thermal calculations, and step-by-step procedures. It was also useless. The manual assumed access to controlled welding conditions, preheating furnaces, stress relief equipment, calibrated thermocouples, X-ray inspection. Kowalski had used hand torches, hammers, and visual inspection. The manual specified allowable steel types, carbon content ranges, and hardness values. Kowalski had used whatever was available. The manual required documentation at every stage: material certification, weld traveler sheets, non-destructive testing reports. Kowalski had documented nothing. The manual attempted to codify improvisation, and improvisation, by definition, cannot be codified. A few sections came close. Chapter 7, Peening for Stress Relief, accurately described Kowalski's hammer and chisel technique. Chapter 11, Low-temperature electrode baking, documented the galley oven method for reducing hydrogen content. But the manual's overall philosophy was wrong. It treated field repairs as degraded versions of proper engineering. Kowalski's approach had been different. Field repairs were valid engineering, just under different constraints. The manual assumed failure was unacceptable. Kowalski assumed failure was inevitable. The goal was controlled failure that didn't kill anyone. The manual was never used. By 1946, carriers were being repaired in Navy yards with specification materials and qualified procedures. The emergency conditions that had necessitated Kowalski's improvisations no longer existed. The manual sat in technical libraries, referenced occasionally by historians, ignored by practitioners. But the question remained: why did it work? In 1952, the Naval Research Laboratory conducted a retrospective study titled Metallurgical Analysis of Non-Specification Flight Deck Repairs, USS Intrepid. The researchers cut samples from the Intrepid's deck during its 1952 overhaul and subjected them to microscopic examination, hardness testing, and tensile testing. Their findings were paradoxical. The welds were defective, porosity exceeding 15%, incomplete fusion in 30% of samples, hydrogen cracks in 40%. By Navy standards, every weld should have been rejected. But the welds had survived 3 kamikaze impacts without catastrophic failure. The researchers concluded that Kowalski's success came from favorable coincidence of multiple suboptimal factors. The porosity and cracks acted as stress concentrators, but also as crack arresters, distributing impact energy across multiple microfailures instead of one catastrophic fracture. The dissimilar metals created metallurgical mismatches, but also created zones of varying hardness that absorbed energy through differential deformation. The peening induced surface compressive stress, which counteracted tensile stress from impacts. The composite deck structure, mild steel over STS over structural beams, created a layered system where each layer failed differently, absorbing energy through sequential collapse rather than sudden rupture. In other words, the welds worked because they were wrong, not despite it. The Naval Research Laboratory recommended further study. None was conducted. The findings didn't fit existing theory, and there was no practical application. By 1952, jet aircraft required stronger decks than could be field welded from scrap. Kowalski's methodology died with the war it had served, or so it seemed. In 1982, during the Falklands War, HMS Invincible suffered flight deck damage from an unexploded bomb. British welders performed emergency repairs using steel salvaged from damaged destroyers and techniques that closely resembled Kowalski's. Preheat with torches, mixed electrode types, peening for stress relief. The repairs worked. The Invincible resumed operations within 24 hours. A Royal Navy engineer reviewing the repairs noted in his report, "Procedures non-standard but effective. Recommend documentation for future reference." But no documentation was created. The emergency passed. The repairs were replaced during routine maintenance. The knowledge remained tacit, held by the men who'd done the work, transmitted through practice rather than manuals. Kowalski's legacy wasn't a written procedure. It was a philosophy. When specifications fail, improvisation succeeds. When materials are inadequate, combinations compensate. When theory says it won't work, try it anyway, because theory doesn't account for desperation, ingenuity, and the willingness to weld under fire. The manual that didn't exist couldn't have existed, because what Kowalski knew couldn't be written down. It had to be learned through steel, fire, and the knowledge that incomplete welds kill men. The Yokosuka D4Y Judy that struck the Intrepid on May 4, 1945, carried more than a bomb. It carried the culmination of Japan's kamikaze evolution. By May 1945, suicide tactics had become Japan's primary naval weapon, refined through thousands of attacks into a calculated science of destruction. The Judy was chosen deliberately. Faster than the Zero, more maneuverable than the Betty, it could evade anti-aircraft fire long enough to hit with precision. Its 500-kilogram bomb was twice the size of standard loads, large enough to penetrate armored decks, detonate in hangar bays, and trigger secondary explosions that would consume a carrier from within. The Intrepid should have sunk. The fact that it didn't reveals less about American engineering than about the unpredictable physics of ship killing. The Judy dove at a 45-degree angle, aiming for the forward elevator, a critical target. Destroying the elevator would cripple aircraft launch operations. Penetrating to the hangar bay below would ignite avgas and ordnance. The explosion would propagate through ventilation shafts, ammunition elevators, and fuel lines, turning the carrier into a floating inferno. Japanese intelligence had studied Essex-class vulnerabilities for 2 years. They knew where to hit. At 15:23 hours, the Judy passed through the Intrepid's defensive screen. 5-inch guns fired proximity-fused shells that exploded around the aircraft, shredding its left wing. The plane continued, now tumbling but still on target. At 400 feet, 40mm Bofors guns opened fire, hitting the engine cowling and cockpit. The pilot was likely dead before impact. The aircraft struck the flight deck at 320 miles per hour. The bomb detonated 0.3 seconds later. The explosion created a crater 8 feet wide and 4 feet deep. The case-hardened armor plate Kowalski's team had welded over the elevator absorbed the initial blast, but the plate's welds failed. 3 of 4 anchor points sheared off. The plate lifted, rotated 15 degrees, and crashed back down. Beneath the plate, the original STS deck buckled. Beneath that, structural beams twisted. The elevator mechanism, 26 tons of hydraulic machinery, shifted 6 inches out of alignment. But the hangar bay remained sealed. The explosion vented upward and outward. Blast pressure radiated across the deck, killing 8 men instantly. Shrapnel from the aircraft and bomb casing lacerated another 20. Fire spread across 60 square meters, igniting aviation fuel residue and paint. But the bomb didn't penetrate. The armor plate, despite losing 3 welds, had stayed in place long enough to deflect the blast away from the elevator shaft. The blast wave traveled laterally across the deck rather than vertically into the ship. Secondary explosions didn't occur because the fuel lines beneath remained intact. Damage control teams arrived within 90 seconds. They extinguished the fire in 12 minutes using foam and seawater. The casualties were evacuated in 20 minutes. By 1600 hours, 37 minutes after impact, the deck was cleared for emergency landings. The elevator was inoperable. Aircraft had to land and remain on deck, unable to be struck below for maintenance or storage. But the Intrepid could still fight. This infuriated Japanese intelligence. Post-war interrogations of captured Japanese naval officers revealed that the May 4th attack had been expected to achieve a mission kill, damage severe enough to force the carrier back to Pearl Harbor for repairs. The Judy had been vectored specifically to the Intrepid, because previous attacks had weakened it, making it vulnerable. Instead, the Intrepid remained on station for another 6 weeks. The reason wasn't superior American engineering. It was Kowalski's unauthorized armor plate and a fortunate alignment of failure modes. The Naval Research Laboratory's 1952 analysis reconstructed what happened. The armor plate, though improperly welded, was thick enough, 1.25 inches, and hard enough, 280 Brinell, to resist penetration from a 500 kilolum bomb detonating on contact. The bomb's blast energy was partially absorbed by the plate's plastic deformation. It dented rather than shattered. When the plate's welds failed, the plate lifted, but didn't separate completely. The fourth weld, a 6-inch section that somehow retained tensile strength, kept the plate partially attached. This partial attachment was critical. It prevented the plate from becoming a 200-pound projectile that would have killed dozens more men. Instead, the plate acted as a blast deflector. It absorbed the upward component of the explosion, then fell back into place, sealing the crater it had created. It was accidental protection. The plate wasn't designed to detach and reseal, but that's what it did. If the fourth weld had failed, the plate would have tumbled across the deck, killed more crew, and left the elevator shaft exposed. If all 4 welds had held, the blast energy would have transmitted through the plate into the elevator mechanism, destroying it completely. The failure of exactly 3 welds was optimal and entirely unplanned. American carrier doctrine after May 1945 incorporated this lesson, but not in the way Kowalski would have recognized. The Navy didn't authorize scrap steel reinforcement. Instead, they accelerated development of armored flight decks for the Midway-class carriers, then under construction. The Midway-class featured 3.5-inch armored decks structurally integrated into the hull. They could survive kamikaze strikes without improvised reinforcement. But they weighed 30% more than Essex-class carriers and required larger engines, more fuel, and reinforced port facilities. They weren't ready until 1945, too late for the war. The Intrepid, with its cobbled-together scrap steel, fought the battles the Midway class was designed for. The May 4 strike was the last kamikaze to hit the Intrepid. Not because Japanese attacks stopped, they continued until August, but because the Intrepid was repositioned to a support role, launching airstrikes rather than operating near contested airspace. The damaged elevator was never fully repaired during wartime. A temporary wooden platform covered the crater. Aircraft landed, refueled, and launched from the deck without being struck below. It was inefficient, dangerous, and unsustainable. It lasted 3 months. Long enough. The Intrepid returned to San Francisco in August 1945 for complete overhaul. Kowalski's reinforcements were cut away, replaced with specification steel. The scrap armor plate was removed, catalogued, and discarded. No one documented where it went. The kamikaze that should have sunk the Intrepid instead became a footnote. One of 3,800 kamikaze attacks documented between October 1944 and August 1945. The attack inflicted casualties, but not mission kill. It damaged, but didn't destroy. And it demonstrated that in naval warfare, survival often depends not on what was designed, but on what was improvised when design failed. The Judy hit with precision. The armor plate held with luck. In war, luck often matters more than engineering. On August 15, 1945, at 2200 hours, the USS Intrepid received the ceasefire order. The war was over. The carrier had survived 1,222 days of combat operations, 5 kamikaze strikes, 1 torpedo hit, and mechanical breakdowns too numerous to count. The flight deck, reinforced with unauthorized scrap steel, had held through all of it. In September 1945, the Intrepid sailed to San Francisco for decommissioning and overhaul. Kowalski's welding team was disbanded. The scrap steel reinforcements were scheduled for removal, replaced with specification materials during what the Navy termed restoration to standard configuration. But when inspectors examined the deck, they found something unexpected. The improvised reinforcements had integrated with the original structure in ways that made removal more difficult than replacement. The welds, porous, cracked, metallurgically suspect, had corroded along with the base metal, creating a fused mass of steel that couldn't be separated without cutting out large sections of deck. The cost estimate for removal exceeded the cost of simply leaving it in place and welding new plates over the top. So they did. The Intrepid was recommissioned in 1954 with Kowalski's scrap steel still embedded in the flight deck, hidden beneath layers of specification plating, preserved not by intent but by economics. The carrier served through Korea, Vietnam, and the Cold War. It recovered spacecraft during the Mercury and Gemini programs. It launched thousands of combat sorties. And beneath it all, the salvaged destroyer plating and case-hardened armor remained, invisible, forgotten, but still there. The Intrepid was decommissioned for the final time in 1974 and converted into a museum in 1982. Restoration crews, preparing the flight deck for public access, discovered the subsurface reinforcements during structural surveys. They left them in place. Removing them would have required cutting through decades of paint, corrosion-resistant coating, and modern deck plating. The scrap steel had become, by default, part of the ship's permanent structure. Visitors to the Intrepid Museum walk across that steel daily. They don't know it's there. The docents don't mention it. The plaques describe the carrier's combat history, the kamikaze strikes, the casualties, the missions flown, but they don't mention the welds. Kowalski never visited the museum. He died in 1997 at age 82, survived by 3 children and 7 grandchildren. His obituary listed him as a retired Navy chief, with no mention of his wartime service. His children donated his personal effects to a local VFW post. Among those effects, a toolbox containing welding chipping hammers, a worn copy of Navy welding specifications, and a handwritten note that read, "Welds don't have to be perfect, they have to hold." The note wasn't dated, it wasn't addressed to anyone. It was just a reminder to himself, a philosophy forged in urgency and tested under fire. Delgado, the welder who finished his work while the deck burned, lived until 2001. He never spoke about the Intrepid publicly. When his son asked him about the war, Delgado replied, "I fixed things, that's all." O'Brien, killed while cutting damaged steel, has no descendants. His service record disappeared in a 1973 fire at the National Personnel Records Center. His contribution exists only in casualty reports and a grave marker that says nothing about how he died. The Essex-class carriers were engineering compromises. Built fast, built many, designed to be replaced rather than repaired. They weren't supposed to survive extended combat against kamikazes. They weren't supposed to be maintained with scrap steel and improvised welds. But they were, and they did. The Intrepid outlasted more sophisticated ships. It outlasted the armoured British carriers that required 2-year construction times. It outlasted the Japanese carriers that prioritized offense over survivability. It outlasted every tactical assumption about carrier vulnerability. Not because it was better designed, because it could be repaired. The mythology of the Essex class isn't its firepower or its armor, it's its maintainability, the ability to take damage, patch the damage with whatever was available, and resume operations. The ability to survive not through invulnerability, but through rapid recovery. Kowalski's scrap steel embodied this philosophy: imperfect, improvised, good enough. Modern naval engineering has moved away from this approach. The Ford-class carriers, commissioned in 2017, use electromagnetic catapults, advanced armor composites, and integrated damage control systems that make field repairs nearly impossible. They're designed not to be hit, protected by layered defenses and electronic warfare systems. If they are hit, they require shipyard-level repairs. There is no equivalent of Kowalski welding scrap steel under fire. This makes them more capable in theory. But theory assumes logistics, resupply, and port access. Combat assumes none of this. The Intrepid fought without assumptions. It fought with what it had: salvaged steel, overworked welders, and a philosophy that acceptable welds were the ones that held long enough. In 2024, the Intrepid Museum conducted structural surveys using ground-penetrating radar. The surveys mapped the subsurface reinforcements in detail, creating a three-dimensional model of every plate Kowalski's team had welded. The model revealed something remarkable. The reinforcements weren't random. Kowalski had prioritized zones based on damage patterns from previous strikes, concentrating steel where impacts were most likely, leaving other areas lighter. It wasn't documented, but it was deliberate. Kowalski had analyzed the tactical threat and responded with structural engineering performed under combat conditions, with no formal training in naval architecture. The museum archived the survey data. There are no plans to remove the reinforcements. They've become historical artifacts, evidence of improvisational engineering that saved 2,800 lives. The deck that wasn't supposed to hold became the deck that couldn't be removed. The welds that violated every standard became welds worth preserving, and the men who improvised under fire became footnotes in a history that emphasizes ships over the people who kept them afloat. But the steel remembers. 80 years after the last weld was laid, the scrap steel from the USS Luce still supports the flight deck of the USS Intrepid, no longer fighting, no longer necessary, but still there, imperfect, improvised, unbreakable. Subscribe to our channel to explore more documented and haunting stories from the machinery of war. Thank you for following this account of the USS Intrepid and the men who welded her together. We'll see you in the next video.